Okay, this is chapter 4.2, measuring strength of association with correlation. We're going to look further into quantifying the strength of the association. So number one, the correlation coefficient is a numerical measure of the strength of the association between two numerical variables. Some facts about the correlation coefficient. First one is that the symbol for correlation is the letter R. Second one is the correlation coefficient is always a number between -1 and +1, and that's inclusive. The sign of R gives the direction of association. If R is positive, then the association is positive. And if R is negative, then the association is negative. The absolute value of R measures the strength of the association. Values of R close to 0 indicate a weak association, and values of R close to +1 or -1 indicate strong associations. Just a quick example here of absolute value. So if we have R equal to -0.55, the absolute value of -0.55 is +0.55. It's looking at just the number part. If you have a correlation of +0.55, its absolute value is the same. So that means these two correlations, -0.55 and +0.55, have the same strength. Okay, so again, strength is just the number part. Ignore the sign. Next one, correlation coefficient measures the strength of a linear association. Doesn't do nonlinear, so we can only use it when we know we have a linear association, which means we're always going to want to look at a scatter plot. Last thing, the correlation coefficient is unitless. So for instance, if we say our correlation is -0.55, we stop there. There are no units that go after it. Nothing that follows it. Nothing like dollar signs or pounds or anything like that. Again, unitless. Okay, number two, some examples. So for example, if your correlation is 0, or if R is 0, that means there's no linear association between the x and y variables in your scatter plot. And the scatter plot might look something like the following. Right? So in this scatter plot, we've got fuel capacity versus the page number. And this is taken from Consumer Reports Car Buying Guide. So if we take a closer look or consider what the variables are, it makes sense. So it tells us that knowing the page number in the Consumer Reports Buying Guide really doesn't help us at all predict the fuel capacity of a vehicle. In fact, this is an example of the weakest association possible. And the weakest association is when you get a correlation of 0. Right. Moving on, next one. If you get a correlation of 1 or -1, so if R equals 1 or -1, that means there's a perfect linear association between the x and y variables, and all of your points lie on a straight line. So you might get a scatter plot that looks like this for a positive correlation. Notice that it's increasing as we go left to right, and all those points fit on a straight line. And on the right-hand side, you might get a correlation that's negative. -1, perfect negative association. Again, all the points lie on a line. So if we take a closer look, each of these points, both scatter plots, represent one student. And what that's telling us in this particular case, the scatter plot on the left, is that if I know your homework grade, I can perfectly predict what your test grade is going to be. And this is hypothetical data. On the right, it tells me that if I know the number of absences, how often you've missed class this semester, then I also can predict your test grade. I can do that perfectly without any errors. And these are examples of the strongest associations that are possible. All right, last one down here. If you get a correlation between 0 and 1, then your x and y variables have a positive correlation. This means that the large x values are associated with large y values, and small x values are associated with small y values. And that is in the scatter plot on the left. So this is a correlation that has a positive sign. Okay. Take a closer look at this. This is price versus size. So this is a scatter plot we've seen before. These were the homes that we got from Zillow.com. And it shows us that knowing the size of the house gives us a ballpark idea of the price of the house. It's not going to be a perfect prediction because there are other factors involved. You might be able to account for some or explain some of those other variables. Location of the house, for instance, might account for the price or part of that price, which is part of that price difference. And then the other one here If R is between -1 and 0, then your X and Y variables have a negative correlation. This means that the large X values are associated with small Y values, and small X values are associated with large Y values. And you might get a scatter plot that looks something like this. And so note there's a downward trend here between city mile per gallon rating and weight. As we go left to right, we see that there's a downward trend. Again, there's a negative association. And in this case, it's not perfect, which means that knowing the weight of a car would help us predict the city mile per gallon rating because there's some strength here. But there would be other variables involved as well. Again, it would give us a ballpark idea of what the city mile per gallon rating is if we know the weight of your car, but it wouldn't give us a perfect prediction. Okay, number 3 is a matching exercise. I'm going to go through the directions, but you may want to press pause after that. I'm going to press pause as well to fill in the answers. Once you've given yourself a chance to try it, you can press play. All right, so number 3, you're going to match the following scatter plots with the given correlations, and the scatter plots can be found in your textbook on pages 149 and 150. All right, so in the top row of this table, I've given you several values of R, the correlation. In the second row, you're going to fill in the letters that match the scatter plots. So keep in mind the strength looks at the vertical variation. If you see less vertical variation, for instance, this has very little vertical variation, then you're looking at a stronger correlation. We also want to look at the direction. So you may want to think of it as picking out which ones have a negative direction first, filling in those first 4, which have a positive association, filling in the 4 on the right, and then narrowing it down, which one doesn't look like it has any direction. That's going to go in the middle. And so again, I'm going to press pause. I'm going to fill in the answers. I want you to press pause and try this out. Okay, so hopefully you've given yourself a chance to try this. I've got the answers in the second row of your table, so you can check to see how you did. And I'm just going to go through a couple of examples. Okay, so for instance, the one in the middle, kind of the tough one to pick out, but E doesn't appear to have any trend in there. It doesn't appear to be positive or negative, so that's our first hint. And the vertical variation in there is very big. You got a lot of spread in the vertical direction. As another example, scatter plot D, there's our perfect correlation. And since it's got an upward trend, this is +1 for your correlation. Let's try one, maybe 2 more. Scatter plot A has a downward trend, not too much vertical variation, so it's got to be a fairly strong correlation. And that is the strongest -1 given. Okay. And let's pick one more. H is a good one. This one has a slight upward trend, so it's positive. Looks like it's got a lot of vertical spread, so it's got one of the weaker positive correlations. It's going back up to the table. Looks like it's the second weakest one, just a little bit stronger than the one to the right of it. Scatter plot I has a little bit more vertical variation. All right, so a little bit more information on the correlation coefficient. First thing is the correlation coefficient doesn't tell you anything about an individual observation. It only tells you about the overall trend. So as an example, if we go back to scatter plot A, and flip back to that, scatter plot A is this one up on the top left on the previous page. Right. This scatter plot A shows that people who started a job more recently, a later start year. So if we go this direction, the years become more recent. They tend to have lower salaries. So as we go left to right, our salaries are tending to go down. Okay. However, there are exceptions. Someone with a later start year may make more money than someone with an earlier start year. So again, this is just telling us about the trend. It's not telling us about everybody in here. So for instance, if we take this person who has a later start year than this person, we can see this person actually makes more money. It's opposite of what we see in the trend. Right, so again, the trend doesn't tell us about individual observations. It just tells us about the overall pattern that we're seeing. Second thing on our list. So I'm back to the next page. Association does not imply causation, and therefore neither does correlation. So as an example, the following scatter plot shows the number of televisions per 1,000 people and the life expectancy for a sample of 22 countries. And this is from the Workshop Statistics book by Rossman and Chance. Question is, do you think that sending more TVs to these countries will lead to higher life expectancies? And what other variables might explain the association seen in the scatter plot? So if we take a look at the scatter plot, We've got life expectancy, I'm going to abbreviate that, versus number of TVs. And we see there is somewhat of an increasing trend here, but it levels out, so this would be nonlinear. Okay. But more importantly, the answer to this first question is no. This is not a causal relationship. In other words, sending TVs to these countries isn't going to increase their life expectancy. So other variables that might account for this, one might be wealth. If your country is wealthier, you live in a wealthier country, probably have better access to healthcare or better medical care. And as you know, the wealth also contributes to having more TVs per person. All right, next one. Strong correlation doesn't indicate a linear trend, and a weak correlation doesn't indicate a nonlinear trend. So always check the scatter plot for linearity before interpreting the correlation coefficient. So I have two examples here. First one, the previous scatter plot is a moderately strong correlation. R is equal to 0.743, so that's on the higher end. And notice that if you look back at the scatter plot, it's not a linear association. So again, after examining the scatter plot, it appears the association is not linear. So you don't want to just stop with a correlation or start here, get your correlation, say, oh, that's strong, must be a linear association. That's not always the case. And you always want to have a scatter plot when you look at correlation. Our second example, following scatter plot shows the hypothetical scores on 2 exams for one class of students. This is also from the workshop statistics book. Correlation is 0.037. So correlation is 0.037. It's awfully close to 0, indicating a very weak association. Question is, do you think the trend is linear or nonlinear? And what would we have missed without the scatter plot? Well, what we see is that most of these students, if we look at their scores, that forms a linear trend. But we have an exception here. We have an outlier. So if we hadn't done the scatter plot, we would have missed that outlier. We would have missed that there was a linear association amongst those other students or amongst those other points. Right, so by the way, in number 5, correlation actually does change. If we take that outlier out, it goes from a correlation of 0.037 to 1. Again, that's when the apparent outlier is removed from the previous scatter plot. So given this information, do you think the correlation is resistant to outliers? Hopefully your answer is no. Turns out that the correlation, I'm going to abbreviate that with R, R is not resistant to outliers. So again, you always want to check your scatter plot.